Hello friends, welcome to UGC E-PG Pathshala. I am Dr. Poonam Sharma, Associate Professor in Geography at Shahid Bhagat Singh College, University of Delhi. Today, I am going to discuss about the module on factor analysis, a tool for synthesizing geographical phenomena. This module is part of the paper Quantitative Techniques in Geography. Let us explore the significance of this tool in geographical research. In geographical research, there is a common problem of synthesizing more number of attributes into a few variables in such a way so that the common characteristics of geographical attributes are to find a solution of a specific research problem. Factor analysis is a technique to analyze the complex multivariate structure of data set to convert attributes of possible correlated data characteristics into a set of values of linearly synthesized variables called latent variables. When attributes of a set are considered as independent, synthesization of geographical attributes is modeled as a linear combination of potential factors plus error. By definition, suppose we have a set of random attributes x1, x2, x3 and xn till xn with their means mean 1, mean 2 and mean 3. The mu's with m observation called number of items of data series or the size of data set, and some unknown constant Lij and k unobserved random variables fj, where I is 1, 2, 3 up till n, it can be n numbers, and j 1, 2, 3 dot k subject to k less than n. We have the equation as follows: x1 minus mu I, xi minus mu I equals to Lij f1 plus Lij fk plus ei. Here in this equation, ei implies error term with zero mean and finite variance. In matrix form, above equation is written as x minus mu equals to Lf plus ei. In this equation, Lf is matrix of factor loading which shows common characteristics, that is commonalities of observed attributes. For example, there are 10 different observed attributes of social structure of 1000 household samples, that is m observations, of a particular caste residing in a region. The attributes are such as sex, age, educational qualification, occupation, marital status of the head of the household, and so on. I wish to analyze the common social structure, that is the common variance of that particular caste and the effects of each factor, the latent variables that are extracted through LF matrix for the analysis of social structure. So, the process of extracting latent roots operative through factor analysis is essentially dependent on its following basis. Number 1, Factor analysis is a multivariate technique where data containing without a dependency but with relationship, and also a tool for synthesizing the variables essences on the basis of their communalities into a factor. Factor analysis is to find latent variables based on communalities H2. Point number 3, factor analysis is based on relationship of variables. Point number 4 says it provides the factors which constitute multivariable characteristics. The structure of these factors is based on common variance and systematic interdependencies among variables of a set. Point number 5, the factor analysis reduces the large number of attributes into a few factors and interprets the common characteristics of these attributes called observed variables. Let us look into methods of inferring the latent roots in the factor analysis. The different methods include number 1, clusterization. It is a simple method of inferring the results of common properties of variables from the given symmetric correlation matrix. Very high correlation values of variables are chosen for the purpose, and on the basis of these values, the structure of a common factor is analyzed. Another method is centroid method. This was proposed by Thurston in 1931. It is simple and easy to extract latent roots even through manually adopting the process given below. These are 5 steps as given below. In order to understand the procedure, an example is given in the last section of this module. The steps includes A. Generation of raw data of geographical attribute to use for analysis of common features of given structure in the data set and conversion of it to standardized form to keep it at free scale. 2. Preparation of correlation matrix of attributes ignoring signs. 3. At step number 3, sum of each columns including diagonal cell values, that is 1 from column sum, summation of column. The 4th step is square root of the sum of the column sum, and at 5th step it is value of common centroid. 1 latent root, that is summation t divided by summation t, which is summation t hat 0.5. The step 2 involves the preparation of cross products of factors, the preparation of cross products of factor 1, that is Q1 matrix. In step 3, to prepare the residual coefficient matrix R1 matrix, subtracting Q1 from correlation matrix. Step 4, extract common centroid 2 from R1 matrix. In the 5th step, you go to same procedure until the entire variance is reduced to minimum. Another method which is popularly used is principal component method. It was used by Hotling in 1933, Haggett 1965, Cole and Smith in 1965, Berry and Pal in 1968, Berry et al. In 1966 in various fields of geographical research. This method is based on linear combination of variables because it finds out the degree of collinearity among the variables and synthesizes the structure of common factor, given in the manner as P1 equals to A1 into 1 plus A2 into 2 plus A3 into 3 and so on till n into n, where P1 is the principal component 1, xn are the variables and n and r and a are the coefficients as the factor loadings. Due to its lengthy process, it is given in a separate module entitled Principal Component Analysis. Here, figure 1 explains the complete procedure and steps which are required to compute a factor analysis. Now, I am going to give you an example. We will use the data and discuss the complete factor analysis on the basis of that data. To interpret the common characteristics of total disabled population in seeing, in India through extraction of latent root of common centroid using centroid method given by Thurston in 1931 of given state-wise census 2001 data for 14 attributes. For generation of raw data, a set of 14 parameters, that is n equals to 14, is related to age-wise percentage data of disabled population in seeing, and the attributes, the operational attributes are attribute 1, x1, x2, x3 and till x14 of state-wise entities of India. Observations R1, R2, R3 till R35 have been collected from Census of India 2001 as coded in the following table. Table 1 gives you the variables chosen for the study, that is the disabled population data for 2001. In the given table 1, you can understand the number of 14 variables that has been chosen. These variables include, and these variables, as it is already explained to you, are coded as x1, x2, x3 up till x14. These include disabled population percentage to the total population, disabled in seeing as percentage of disabled population, disabled in seeing main workers as percentage of total disabled population, and then further data is been categorized as per the different age groups. For example, 0 to 4 years, disabled in seeing 0 to 4 years, 5 to 9 years, 10 to 19 years, 20 to 29 years, 30 to 39 years, 40 to 49 years, and at this bracket of 10 years, it has been, the data which has been taken is up to 90 years and above. Now, I will also share with you these variables and what are the states that are covered. Look at table 2. Table 2 gives you the areas, the states that have been covered. These include 35 locations of our states and union territories, and these are marked as R1, R2 up till R35. In table 3, you can see that how the data is been arranged in the form of a matrix. In table 3, you can see R1 to R35 as rows and X1 to X14 as your columns, and you can read from the data R1 X1, you can read the data, it is 2.98. If you similarly, you can see any other row and column, say for example R4 and X5, it is 8.99. And also, if we compare the data, if we look at and try to understand the data, that is for region 10, that is R10, and if we run to see the X7 variable, for X7 variable for R10 is 13.46. So, you see here that in terms of various locations, various spatial units, various spatial zones, and the data are put in the form of a matrix. Now, I am taking you to table 4. Table 4 gives you the conversion of raw data to the standardized scores as ZScore matrix. Here, the magnitude of each attribute is transferred. The magnitude of each attribute is transformed into standard score to make the scale. Here, magnitude of each attribute is transformed into standard score to make scale-free distribution with zero mean and unit standard deviation. It is formulated as Z equals to x minus mu divided by standard deviation. Transformed values of each and every attribute is given in the following table. Let's glance through table 4, which gives you the ZScore matrix. Here, the variables and the spatial units, variables and the spatial areas, the variables and the spatial location Z-scores are being given. Now, you can understand and go through the table once and try to understand how it has transformed from your original data to the Z-scores. Now, I am going to take you to table 5. Look at the table 5. It gives you symmetric correlation matrix of a given n into n size. If we look at table 5, the symmetric correlation, look at X2, the correlation shows 0.4. Similarly, if you look at X4, it is 0.23, again a very low correlation. Now, scroll down and see, scroll right and see X5 factor and X6 factor, the relationship is 0.81. Similarly, you can also see X7 and X11, the relationship is 0.7. Factor loading 1, it gives you the value 8.91. Let's look at table 6. Factor loading cross product 1. And you can see here that how certain factors are coming up as a significant towards our results. Have a glance at table 7, that is the residual matrix. Here the signs are ignored, which means R1 equals to R minus CR minus 1. The residual matrix explains that how much things remain there which are considered unexplained or residual. Table 8 gives you factor loading matrix for two common factors. Here, if you look at carefully, on your left, in the column you can place our x1 to x14 factors, and in the columns you see column 1 factor 1, factor 2 and squared values of factor 1 and factor 2, which over here commonalities are also given. The eigenvalues and the percentage variance can also be compared and understood. It clearly indicates that factor 1 has a value, eigenvalue of 6.0106, while for factor 2 it is 2.59. If we see the variance, you see the variance explained. For factor 1 it is 69% and for factor 2 it is just 30%. Let us see how to interpret the results of factor analysis. Characteristic features of common factors of processed data set are explained below, are explained here. Number 1, common factor 1 is enough stronger that accounts for more than 2/3 strength of total variation, that is 69.85% of all the 14 attributes considered for the present analysis, while factor 2 includes about 1/3 share of the total variation, that is 30.85%. Second, aged and two-aged disabled population, that is above 60 years of age, contributes positively, and disabled population of growing children and teenagers, that is 5 to 20 years, contributes negatively to common factor 1. As a result, the name of this common factor has been assigned as disability of aged population, which is more prevalent in almost all states of India. The common factor 2 is negatively related to the strengths of disabled population in the population with the adults disabled in seeing population. It accounts for 30.85% of the total variation. Therefore, it may be named as disability in adult population. That is an important feature of distribution pattern age-wise disabled population in India. The last column of table 8 shows that attributes X11, X12 and X13 are most important to conclude higher degree of common variance in the present factors. Scatterness of these two common factors shows that there is emergence of two group of factors. Number 1, children and teenagers. Disability has positive effect in factor 2. Number 2, negative effects in factor 1, while remaining attributes form opposite group in the distribution. The figure 2 shows you the scatterness between common factor 1 and 2 in the disabled population in India. Factor analysis highlights common features of a given set and n attributes for m observations. In the above example, common factor 1 accounts for the highest variation of the set of data. It is obvious that two common features of different age groups, disabled population in India, emerges as 1, aged group and two aged group and two aged disabled population form stronger bonding in the population distribution, and number 2, the children and teenagers disability is dependent on their socio-economic status. That's all for the day today. In this session, I hope you have understood the concept of factor analysis as a tool for synthesizing geographical phenomena. I hope the session proved fruitful. Thank you for visiting and watching the session. Goodbye.